commutative. Theorem number 3 is distributive. That's the one which gets tricky, because if you look at the O version of distributive, it's totally different. Then we had theorem 4, which is identity and null element. Let's now look at theorem 5. Okay, theorem 5. So let's note today's coordinates. So it's week 4, lecture 2, and today is the 13th of April 2022. Yeah, is that correct? 13th April? Okay, now for some of these diagrams, so for the next one, I'm going to switch over to the computer. I've placed okay, let's switch over to the computer, and yeah, all right, this is it. So the way I've done it is so that we don't have to draw much, but you will still have to draw. It's only that I'll be faster in delivering your content. All right, guys. Okay, so we've done all these gates. Theorem 1, associative law. We've looked at this yesterday. Basically, I was drawing this yesterday. I was doing it with the hand. Commutative law. Done this yesterday. Distributive law. You see, for those of you who think of the O as a plus or addition, and think of an AND as a multiplication, for the O version, it's fine. You know, you say, oh, we're expanding. But when you come to this version over here, it's different. So that is the reason why I repeat, and once again, I keep on repeating, and I was correcting everybody in my lectures, that hey, this is not a plus, this is not addition, this is O. And when you write it down, you don't call it plus, you say O. And this dot is not multiply, you say AND. All right. So if you look at this, your earlier rudimentary mathematics does not fit into that. Okay. But you can prove it, as we did, using truth tables. So theorem 1, 2, and 3 we can prove using truth tables. Okay. And we did that. All right. Where I gave you homework. So for every theorem, you're supposed to prove it with truth tables. So this is just a summary. A or 0, anything odd with a 0 will always be itself. Anything odd with a 1 will always be 1. So 0 is the identity element for the OR gate, and 1 is the null element for the OR gate, which means whatever you OR with 1, the output will always be fixed to 1. So that becomes a null element. And for the AND gate, right, 1 is the identity element, so that if anything is ANDed with a 1, if you AND anything with a 1, then you'll always get the same input. And if you AND anything with a 0, you will have a fixed output, which is the logic 0, and that's why we call 0 is the null element for the AND gate. And we wrote that down in yesterday's lecture. Okay, now let's look at theorem 5, complement, right? Complement. If you OR anything with its opposite. So the way to prove it is, how do we prove it? Well, let's take the number 1. Let's take logic 1, right? Let's take the O version. If we take logic 1 and what will this become? A bar. If A is 1, what will A bar become? It will be 0. So 1 or 0 will give you 1. Yeah? Okay? Okay, let's take the other opposite. There's only, how many inputs are there in this case? Effectively only one input into this system. Well, the gate has 2 inputs, but if you look at this system, it's only 1 input, right? So if you OR only, if there's only one input, there are only two possible combinations. Either you can have a 0 or a 1. A can either be 0 or A can be 1. Okay, so if it is 0, then A bar will be 1. 1 or 0 will give you, so the two inputs coming into here will be 1 and 0. 1 or 0 will give you 1. Right? Okay, let's say if the input was a 1, if A was 1. If A is 1, A bar will be 0. Right? So over here, what do you receive at the gates? You have 1, 0. 1 or 0 will give you 1. So if anything odd with its invert, anything odd with its invert or its complement, remember 1's complement, that's why we call it complement. Complement is another word for invert, right? If anything is odd with its invert, the output will always be 1, right? Okay, let's now repeat the same for the AND gate. For the AND gate, in this system, if you look at that system, the gate, how many inputs into the gate? 2 inputs, right? How many inputs into the system? Only 1 input. If A is equal to 0, if A is equal to 0, right? Okay, if A is equal to 0, then what will this A bar be? It'll be 1. So what's the 2 inputs coming into the gate? It'll be 1 and 0. So 1 and a 0 will give you 0. So that's an error. Okay, so let me just correct that straight away. That should be 0. All right. Okay, so that's why we got that part right, we just didn't get them. Okay, what if the input is 1? If the input is 1, A bar will be 0. 1 and 0 will give you 0. Right? And what rule do we rely on in this? We also, how do you prove it? You just prove it because there's only 2 inputs. You prove it using truth tables. All right? So this is again a fundamental one. Okay, let's now, so that was theorem 5. Theorem 6, idempotency. Idempotency. Idempotency is when the 2 inputs of the gate are tied together. This is what you call tying the inputs. Can you see? When you tie the input. So effectively, both the inputs are the same thing. Right? When you mirror the inputs or when you tie the inputs. Okay? So effectively, for this 2 input OR gate, what are the 2 inputs going in? It's A and A. Right? So let us say if A is 0. If A is 0, what will be the 2 inputs going into the gate? It will be 0 or 0, right? 0 and 0. So 0 or 0 gives you a 0. What if this was 1? These two will become 1. 1 or 1 will become 1 or 1 will give you 1. So anything odd with itself, A or A, will give you A. Right? Okay. Let's now have a look at this side here. Let's look at the AND scenario. For every theorem, note, there's always the AND version and there's always the OR version. When you looked at idempotency, when you looked at complement, when you looked at distributive, commutative, you know, associative, all of them had 2 versions. The AND version and the OR version. Always you've got to keep track. And sometimes they differ. All right? Okay, now, there's only one, this input, the inputs are tied together. Right? The inputs are tied together in this case. Okay, so if A is 0, both the inputs become 0. 0 and 0 will give you 0, which is same as the input. If A is 1, both the inputs here, they'll come here, 1 will come here, 1 will come here. Both the inputs become 1. 1 and 1 will become 1. So the input is equal to output. So A and A will always give you A. Or A or A will always give you A. So that's idempotency. Idempotency. All right, involution. Involution. Involution is when you have a double bar. All right? If you have A, you put it through an inverter, what does that become? That becomes A bar. Right? And you put it through another inverter, that becomes A double bar. A double bar is the same as A. Okay, let's try it out now. Let's try 0 over here. 0 through an inverter becomes what? 0 bar is equal to 1. 1 through the inverter again will become, 1 bar will become 0. So don't you end up with the same thing again? Right? 1 bar is 0. 0 bar will be 1. So input is equal to output. So involution is the concept of when you have a double bar, right? When you have a double bar, you have the same thing, right? So guys, I want you to note this notation over here. Take a look at this notation. When you have a prime is another way to put a bar, right? The prime is another way to put a bar. So I think, no, we didn't have any primes. No primes here, no primes there. Okay. Okay, so when you have a prime is another way to put a bar. Okay, that's another notation, another way of writing it. Okay. Everyone okay with this? Theorem 7? Theorem 8, absorption. Let's now talk about theorem 8. Okay, so what it's saying here is, so up till 7, guys, everything made common sense, or you could prove it using a truth table. Now theorem 8 is where we break away, where we start to use all the theorems which we have learned from 1 till 7 to prove theorem 8. Okay, so until theorem 7, everything is fundamental level, fundamental theorem, which means you can only prove it using a truth table, or something like you have to try all the inputs, and like what we've done with 4, 5, and 6, right? 4, 5, 6, and 7, right? Actually done the truth tables and see, okay, if it's A is 0, then that becomes 1, then that becomes 0, so A is equal to A. Yeah, we've had a look at that. Okay, now theorem 8. Theorem 8 is absorption. Absorption means A or A and B is equal to A. So what that means is that these two circuits, you can remove it. So this particular circuit is the same as just placing A input over there. All right? Okay, so you can get rid of that entire thing. B was not needed. So let's look at the proof. Theorem 8. Let's look at the proof. Okay. A or A and B is equal to A. What is the proof? Oh, okay. There's reflection from the lights, right? Where's the lights? Nothing to do with these lights. Better? What about if I turn off these lights? Better? Or what about if I turn off these lights? No? I don't know. Is that readable now? Yeah, okay. Contrast, eh? Okay. All right. Okay, let's look at the proof. On the left hand side we have A or A and B, and we've already stated that is equal to. What is the proof? Well, according to the distributive law, we can think of this A. According to the identity rule, you can think of that A as A and 1, right? This A here, and that's A and B. Now, right, according to the identity rule. So that's what I've done over there, right? Okay, so the usual way, what people do is they write down the name of the rule or the theorem beside what they've used. Okay, now, according to the distributive property, we can now have that as 1 over b. Yeah. Now, then, anything odd with a b, according to the null element rule for the OR gate, remember the null element rule, which number was that? So, always you should remember theorem number. Theorem number, what is this? Null element, I think it was 4, yeah? Null element 4 for the OR gate. Anything odd with a 1 will give you a 1. Now, according to the identity rule for the identity, that's theorem 4, always remember the theorem number, you've always got to flip back. The theorem for the null for the AND gate, identity element for the AND gate, A and anything ended with anything with 1 will give you a same answer. That's the proof. That's the proof. Okay? So what we are trying to say here is, in our previous thing, you have A and B plugging into a system. Now, only your A will plug in. Maybe I forgot to draw a line over there. Right? Only an A will plug in to the system. Only A will plug in. All right. So before you've got this output, let's say, goes and connects to an LED. Let us say this output here connects to an LED. So now what you're doing is, by reducing the system using the absorption rule, we can get rid of all this and just connect that A to an LED straight away. Yeah, whatever was connected over here goes directly over here. Set? Okay. All right. Now let's have a look at the next rule. Okay, absorption. There is another version of absorption which is not on the thing. Another version of absorption is A and A or B is equals to A. All right. Same thing, similar to before. Remember, every theorem has got two versions. One is the AND version and one is the OR version. Okay? So you have A and A or A and B. Okay? Now what do we have for A and A? A and A will be what? Anything ended with itself. Which one do we do looking at? Idempotency, theorem number 6. Anything end with itself will give you the same. Right? Set? Okay. Now then, that is the same as what we've done earlier on. Okay. Same answer. Right? Of course, for all of these, make sure you leave some space. I'm spreading my writing out a lot. I want you to leave some space. I want you to draw the circuit diagrams. I want you to draw the truth tables, all right, to prove it. So I've proven it algebraically. Over here on the screen, the proof has been done using Boolean algebra. But you've got to prove it also using truth table to make sure that I'm not lying to you or I'm not fooling you, right? Prove it using truth tables, right? So make sure you draw so for homework, make sure you draw the circuit diagrams, make sure you draw the truth tables to prove it as well. Okay? Some of them, the circuit diagram is already on the thing, you can copy it. For this one, the circuit diagram was not shown on the PowerPoint slide. All right, now let's have a look at theorem 9. Okay, it gets interesting now. Theorem 9. All right. Theorem 9. Okay, this one does not have a particular name. A or A bar and B is same as saying A or B. Very interesting. All right, let's look at the proof. Let's look at the proof. Now we will need to use some of our earlier thing. All right. Okay, so this was version 1. Set? Yeah? Okay, how do we prove it? Now, this is the key element here, guys. Which one should we use over here? So maybe recall theorem 3 part 2. What does it say? Theorem 3 part 2. It was x or yz, same as saying x or y, x or z. Remember this one? Well, maybe I gave it to you in terms of A and B, but it's the same thing. You are engineering students, remember that. Always remember that. Some of you should have been doing medicine, right? That's what I'm thinking of. You guys are almost as good as medical students, right? Except for we do a 4-year degree and we do a shorter degree, but the level of challenge, the level of psychological challenge is still the same, almost the same. Right? They do a few more years, 1.5 year extra, and that's all that is different. All right, let's prove this. All right, so on the left-hand side, we have A or A bar and B. How do we prove this? Well, according to theorem 3, you've got to have this theorem. Remember, this is one of the theorems where it doesn't work out according to your rudimentary mathematics. This is the one which I keep on repeating. This is where it breaks away. Okay? So if this breaks away, then all your proofs also break away. All right. Okay, so according to this, see that? Let's now expand that way. There will be A or A bar and A or B. Set? Everyone happy with that? What we've done is we've expanded according to theorem 3. All right. Anything odd with its invert, complement. Remember the rule for complement, OR gate complement. Theorem number 5? Yeah. A or A bar equals what? 1. Right? Now, 1 ended with anything gives you, according to the rules of identity, will give you same. And that's our answer. Set. Okay? Let's now have a look at another one. A, let's write that down in your exercise book before we go ahead and prove it. Number 2. What do we have? That's A, what is it? Theorem 9, the second one. A and A bar or B will equal to A and B. Okay? Proof. A and A bar or B, right, is on the left hand side. Now, according to the distributive property, we now expand that A bar and A or A and B. A and A bar, according to complement, what do you get? A and A bar will give you 0. According to identity of OR gate, 0 or A and B. Anything odd with the 0 will give you the same. There we go. Answer. That's the proof. Okay? Right, of course. Homework. Make sure I don't need to write it down each time. All the circuits and the truth table. So make sure when you write it out, you're leaving space for each of those. All right? Okay, because this will come in your test or exam. I will ask you to prove certain things. Okay, let's go to theorem 10. and it says A and B or A and B bar is equal to A. Let's prove it. All right. So I'm going to quick over. So we've got to be fast, guys. We've got to A and B or A and B bar. That's on the left hand side. Okay. Now, according to the distributive property, right, I hope you're writing down the names of the properties which I'm using, right? Make sure, sometimes some people write down distributive, sometimes people say theorem 3 or something. Make sure on the right hand side over here, you're writing down which rule I'm using, all right? Okay, according to the distributive property, you have A and B or B bar. Now, anything odd with its complement is equal to, according to the rule of complements, anything odd with its complement will equal to 1, and then that is A. Anything ended with an A is A. All right. Let's have a look at the camera again, I mean the PC. Right, A or B, let's look at the next one for theorem 10. A or B and A or B bar is equal to A. So for every rule there is always an N version and there is O version. Can you see? All we're changing is the gates. So over here we had a different arrangement, but it's the same concept. Let's come back here. Let's prove this. All right, left hand side. A or B and A or B bar. In fact, by now, because we've got so many rules in the bag now, we can possibly do some reduction. Now, at this point in time, we can have multiple pathways. One pathway is you can do A and A, B and A, A and A, or B and A, or B and B bar, or B and A, right? Okay. You can expand out like how we would do in rudimentary mathematics. But in Boolean algebra, we will use theorem. Which theorem you want to use, guys? Okay, which theorem you want to use? Remember this one. Theorem 3, 2. Once again, we're using this guy. Can you see? Sometimes this guy comes to the rescue. Otherwise, you will get caught. So it was x plus yz is equals to x plus y x plus z. Okay? Now we will go reverse. Remember this one? We used it just early on. Where did we use it? We used it in theorem 9. Now we're using it in theorem 10. So we go backwards. What would that be? There will be x, not x, A or B and B bar. Right? Okay, you see what I've done? All right. Anything ended with its complement. Anything end its complement will be 0. So that's A or 0. Anything odd with a 0 will be the same. There we go. That's your proof. Okay. So you've got to, if you choose the wrong pathway, you firstly can come to the wrong answer if you choose the wrong pathway. Secondly, you can make your problem very, very, very long. This is a much faster, much shorter way to get there. Okay? All right, let's look at theorem 11. How much do we have to go? 11, 12. Oh, right, nice. 11. We're almost there, guys, almost there. But I think I didn't type 11b. All right, 11. Nice one. Boy, look at that one. Theorem 11. A and B, or in brackets A and B bar and C is equals to A and B or A and C. All right? Okay. Theorem 11. Set. What is the proof? Proof. Document camera. Let's write out the left hand side. A and B, or A and B bar and C. Set. All right, left hand side. Okay, interesting. Now, according to the distributive property, your A comes out. According to the distributive property, your A comes out. Then what are you left here with? B or B bar and C. Happy with that? Okay, now, what rule can we apply here? B or B bar and C. Right, let's go back. Let's go back. B or B bar and C. Anything with it? All right. B or B bar and C. Theorem 9, number 1. Right, theorem 9, number 1. Have a look at that. B or, yeah, so that would be theorem 9, number 1. B or B bar and C would be the same as B and C. Yeah. So this would become, sorry, B or C. Set. Everyone see what I've done there? I've used an earlier theorem. I've used one of my earlier theorems, theorem 9, number 1, in order to go from there to here. Set. Okay, now, because our proof wanted it to be in this particular fashion, we just say A and B, or A and C. Okay. All right, alternative proof. Sometimes one proof isn't enough. Hey, by the way, guys, by the way, have a look at this. Left hand side, how many gates? 1, 2, 3, 4. Right hand side, how many gates? 3 gates, right? And left hand side, the problem with the left hand side was what? The left hand side was inconsistent type of gates. You have a 2 input AND gate, you have a 3 input AND gate, you have a NOT gate, and then 2 input OR gate, right? Remember, usually when you pick up a chip, you guys did this in the lab or going to do this in the lab, one chip will have 4 gates. One chip, they'll package 4 gates in the same chip. So you want to use least number of chips, right? Okay. So this will be done in 2 chips. This will be done in 3 chips. 4 chips, right? Okay. Why did I say 2 chips? Well, even though these 2 are separate gates, they can sit on both one chip. Usually it's a quad chip. A quad chip means one chip will have 4 gates. Let me show you this. This is very important. Okay, this is the example. Okay, have a look at this one, guys. This is the IC number 7408, 74LS08. That's the number, right? You guys, maybe if you started EN001, you'll become familiar with this. And in that one chip, there are 4 gates. So even if you're just using your circuit only needs 1 AND gate, you still need to buy 1 chip, right? You still need to buy 1 chip. Like, how many condoms in 1 packet? He doesn't use them. Okay, all right, good boy. Okay, all right. So let's have a look at this. Okay. Alternative proof. It's alternative, but it's the long cut, okay, the long cut. Okay, so yeah, I'm doing the same thing. I've just made it uppercase, but just to show you that there's a difference. B or B bar and C. Okay, we're consistent up till there. Okay, then some people would go the long cut. They would use the distributive property, theorem number 3.1 or something along those lines. 3.1 or which one was it? Let's see the number. Yeah, maybe theorem 3 part 1. So they will do this, something like this. For your homework, you identify which rules I've applied there. I'm using the rules which I've taught you. Nothing different. Okay, so that's A1 over there. And then that's A. There we go, guys. Now the rule which was, I think we're using theorem 3 over here. For the alternative proof, we're using theorem 3 number 2. Theorem 3 part 2. Right, if you wanted to use that. Okay, but it's a longer cut. Why use theorem 3 part 2 when we can use theorem 9.1? All right. Okay. Let's look at theorem 12, guys. Last one. Last one before we do some real hardcore problems. Okay, where did my PowerPoint go? Okay, right. Here we are. All right. De Morgan's. Okay, De Morgan's theorem is basically how you can convert a NOR gate to an AND gate, right? How do you do the conversion? So the De Morgan's theorem comes in two versions. So let's switch to the document camera. Okay, this by the way, guys, this slide is on the Moodle shell, right? Not updated, but it's same one. Theorem 12. De Morgan's. Okay. A or B whole thing barred is the same as saying A bar and B bar. All right. Now, what it actually means is, as the picture shows, if you've got a if you don't have a NOR gate, you see this is a NOR gate over here. Let's say you go to the technician, hey, I want a NOR gate for my second. Technician says, no, I've got only NOT gates and I've got AND gates. So what do? You can build your NOR gate by using this, right? And that's the symbolic method. So let me flip over. So that's the particular circuit symbol which you use. So it's basically your NOR. You have replaced it with, you take your A, you put that, you take your B, you put an inverter, right? Okay, there we go. Set. All right. Okay, make sure you check this out with the truth table. And of course, the symbol for this is, you put a bubble on the input. So in the end, that there is the same as this here. Now there's another version of De Morgan's rule. Another version which isn't mentioned in the slides. So sometimes the slide is missing some things, that's why you've got to come to the lecture. All right? Okay. A NAND B. Let's say you require a NAND gate somewhere, and you go to the technician and say, I need a NAND gate for my thing. Or you go to the shop and you want to buy a NAND gate and there's no NAND gates. So what do you do then? Well, okay. Now, the way to remember this is, you break the bar and you change the sign. Always say that to yourself. You break the bar and you change the sign. Can you see? I've broken the bar and I've changed the sign. Break the bar, change the sign. All right? So that would be, that's your NAND gate. Right? Obviously that will be something like this, and then now you have an OR gate. And the proper symbolic way to write this is, to draw that, is something like that. Set, break the bar and change the sign. All right, let's do one last one before we knock off for this afternoon. Oh no, we got 30 more minutes to go. All right, okay. Theorem 13. Everyone okay with De Morgan's? De Morgan's was easy. Okay, how do you prove it, guys? How do you prove De Morgan's? Yeah, truth table. Truth table. The circuits I've already drawn for you. Okay, truth table. Make sure you have the truth table. That's how you prove it. This is again a fundamental one. Maybe I should have placed it along with 1, 2, 3, 4, 5, 6. I think up till number 6 or 7, it was all fundamental. This is also a fundamental one. A fundamental theorem is one where you can't really break it down. Like for example, number 9 and 10, we use some earlier proof and we prove it using algebra. For De Morgan's, we can't prove it using algebra. You have to go to fundamental truth table level and then say, oh, this column matches this column, therefore this is same. Yeah, we did this in the tutorial this week. Okay, now theorem 13. It is called consensus. Right, consensus. Okay, x and y. Okay, so I'm just flipping around some of the variables, so it's not always about a and b, right? X bar and z and y and z is the same as x and y or x bar and z. Okay, so we want the proof. So look at this. This is a very long one. Okay. X and y, x and z. Now have a look at this, guys. Very same as saying 1 y z. Yeah, we've introduced a 1 there. Doesn't change anything. Okay. Now what can we say about 1? 1 is the same as x or x bar yz. Yeah, that's the same as 1. We can say that this guy here is 1. Set? Everyone happy? Okay, now we expand. If we expand this, that becomes xyz or x bar yz. Yeah? Okay, put the, yeah, okay. All right, now let's now rearrange. Rearranging is what? We say rearranging in mathematics, but in Boolean algebra, rearranging is what? Associative property. All right, so we have x and y or x and y and z or x bar and z or x bar and y and z. Yeah, okay? All right. Now we use the distributive property. Yeah, distributive property. That's x and y comes out and you have 1 o z. And over here you have x bar and z come out and you have 1 and y. Anything odd with a y, right? Everyone with me? Everyone with me? Anything odd with a y is 1. Anything odd with a 1, sorry. Anything odd with a 1 is 1. Anything ended with a 1 is the same. There we go. That's our answer. And we have proven this is consensus. So in consensus, what happens is that one particular term falls off. Can you see? One of the term fell off. And you ended up with just the first two terms. Right? But it's got to be the right combination. Okay? Okay, another version of consensus. Remember, every theorem has two versions. Let's now have the O version. Okay, proof. Okay, what we can do is one way to prove it. One way to prove it is we expand using the distributive property. Here. Okay, so let's have a look at that. Let's do the top side. A and A, or A and B bar, or A and C, or B and A, or B and B bar, or B and C. See what I've done here? Just expanded using the distributive property. Now A and A will be, tell me, what is A and A? A. A and B bar, you can't do much. A and C can't do much. I'll just rewrite that using the commutative property, just make that AB. B and B bar will be a 0, B and C. Okay, now let us now collect everything with an A to one side. Right, so we have A and we have A and B bar, or A and B, that's similar. We put A and C on this side, 0 falls off, and B and C still remains. So have I missing any terms? When you're dealing with so many terms, you've got to keep track. 1, 2, 3, 4, 5, 6. Yeah, and this guy falls off. So now 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, right. Okay, set. So we now, what can we do here? We leave that A alone. This is A into B bar or B, and we have this as C into A or B. All right, okay. Okay, now B or B bar would be 1, right? A and 1 is what? A. A or A is? A or A is? A. Can be further reduced, guys. Now, I'll take this jump. You'll say, how? Okay, proof. It's like proof within proof. Proof within proof. Let A or B